Today we are going through Physics 062541 May-June 2022 paper. Question number 1. A car of mass m is traveling along a straight horizontal road at a constant speed v. At time t equals 0, the driver of the car sees an obstruction in the road ahead of the car and applies the brakes. The car does not begin to decelerate at t equals 0. Part A says explain what is meant by deceleration. So the simplest definition for deceleration is going to be deceleration is negative of acceleration, and that is going to be change in velocity per unit time, and we'll get 1 mark for this and 1 mark for this. That's how you get 2 marks. Part B says suggest one reason why the car does not begin to decelerate at t equals 0. So the reason why the car does not decelerate at t equals 0 is that there is a reaction time for the brain. It might be like 0.1, 0.2 milliseconds or something, but there is a reaction time for humans in which they react to the situation. So that's why it can never be at t equals 0. So we can write here human reaction time, and we'll get 1 mark for this. Part C says figure 1.1 is a distance time graph for the car from t equals 0. Here we have distance on the y-axis and time on the x-axis. Part I says state the property of distance time graph that corresponds to speed. Well, we know that speed is the gradient of distance time graph. So we can write here gradient of distance time graph is speed, and we'll get 1 mark for this. Part 2 says using figure 1.1 determine the initial speed of the car. As we know from part I, the gradient of distance time graph is going to be speed. So for finding out the gradient, we can use the formula y2 minus y1 divided by x2 minus x1. And we are going to take 2 points. So this is going to be our x2, and this is going to be our y2. This is going to be y1, and this is going to be x1. So we can just plug in our values here, y2 minus y1, which is 22 minus 0, because this one box represents 2 for y-axis. So we take that as 22 over here. So y2, which is 22 minus 0, divided by x2, which is 1 minus 0, is going to give us our answer as 22. So we can write our speed as 22 meters per second, and we'll get 2 marks for this. Part D says when the car is decelerating, there's a constant resistive force F on the car due to the brakes. The deceleration of the car is greater than F divided by m and is not constant. Explain why the deceleration of the car is greater than F divided by m. So the reason why the deceleration is greater is because when the car is decelerating, if we draw a diagram over here, this is the car which is moving on this side, and when we apply brakes, the car stops. Like here, the force for the brakes is going to be backwards. So what's going to happen is we also have air resistance acting on the car, which is going to increase the deceleration. That's why the deceleration is more. So we can write here air resistance increases deceleration, and we'll get 1 mark for this. Part 2 says explain why the deceleration is not constant. So for this explaining that the deceleration is not constant, we know the formula acceleration equals velocity divided by time, right? And acceleration and deceleration are both considered as same, just the magnitude is different, because you could say the direction of the force is different. That's why we call it deceleration. So here what happens is, you can see according to this formula, acceleration is directly proportional to velocity. And since when breaking down, what happens is the velocity decreases, the acceleration or deceleration of the car also decreases. If you see here, we have a car over here which is moving on this side at 2 meters per second square, maybe, is decelerating at this rate. When there is air resistance and other stuff as well, which is acting on the car, what happens is after some time, the car will decelerate to maybe 1 meters per second square, and eventually it will become 0 meters per second square because there is no force acting on the car. So that's why we can write here, as the velocity decreases, the air resistance on the car decreases, and hence the car stops. As the velocity decreases, the air resistance on the car decreases. And further to explain this point, what we can add is that the car stops. And if we draw a graph for this, what will happen is, maybe if we say that this is y-axis and this is x-axis, right? If we consider this as 2 meters per second square, what will happen is after some time it will decrease to 0. It won't be in a straight line. It's not constant. It's a decrease in acceleration. And that's how we represent this in graph. And this is the reason why the deceleration is not constant. And we are done with question number 1. Question number 2. Figure 2.1 shows water stored in a reservoir behind a hydroelectric dam. Here we can see the reservoir, and you can see the height of the water, probably 150 meters. And then here's the generator turbine. And part A says state the form of energy stored in the water in the reservoir that is used to generate electricity. So as we know about this, that it is stored in gravitational potential energy, which is known as GPE, or you can write the full form as well. You'll get 1 mark for that. Part B says the turbine is 150 meters below the level of the water in the reservoir. The atmospheric pressure is 1 into 10 raised to the power 5 Pascal, and the density of the water is this. Calculate the total pressure in the water at the turbine. So what we have to do is, we have been given with height, which is this, h, and we are given with density, which is known as rho, and we have to find pressure. So we have the formula: pressure equals h rho g. Height we know is 150, and density is 1000, and gravitational constant is 10. So we get this: 150 into 1000 into 10, which is going to give us our answer as 1, 2, 3, 4, 5, 6. 1.5 into 10 raised to the power 6. And since it's asking for total pressure, calculate the total pressure. So we have to add the atmospheric pressure with the pressure we calculated here. So it's going to be 1.5 into 10 raised to the power 6 plus 1.0 into 10 raised to the power 5. So the same thing we do here as 1.0 into 10 raised to the power 5, and we add it. So we get 1.6 into 10 raised to the power 6. So our final answer is going to be 1.6 into 10 raised to the power 6. And don't forget to add your units, which is for pressure PA, and you'll get 3 marks for this. Part 2 says the turbine has a cross-sectional area of 3.5 meters square. Calculate the force exerted on the turbine by the water. So we have the formula P equals F divided by A. We're given with the area here, which is 3.5. We calculated the pressure in the previous question, which is 1.6 into 10 raised to the power 6, and we have to find F. So that's easy. You just rearrange your formula and you get F equals P into A. A we have is 3.5 into pressure, which is 1.6 into 10 raised to the power 6, and we can get our force here. 3.5 into 1.6 into 10 raised to the power 6, which is going to give us our answer as 5.6 into 10 raised to the power 6. So it's going to be 5.6 into 10 raised to the power 6. And we can write down here the same thing, plus the units, which is Newton for force. And you get 2 marks for this. Part C says the water flows through the turbine through a pipe of constant cross-sectional area. Explain why the kinetic energy of the water in the pipe remains constant as it flows through the pipe. So here we can see a big word, which is constant cross-sectional area. Now what does this mean? This essentially means that the pipe is straight, like this, and both ends have probably the same height. And we would consider the same thing for the whole pipe. It would have the same height. And if it was not a constant cross-sectional area, the pipe would have been like this. The height here will be different, and height here will be different. So the water flow here compared to here will be less or more, depending on the kinetic energy. It's going to be more probably, because that is the shorter end. So the velocity of the water will be more. So since we know the kinetic energy formula is half mv square, and we even know that kinetic energy equals gravitational potential energy. Kinetic energy equals GPE. Since the height is same, and we could say, probably assuming it's a constant cross-sectional area over here, the water flow remains the same amount of water flows from the pipe for every single second. So the velocity of the pipe will remain same, and we can see here the mass will also be remaining same, and the only thing which affects the kinetic energy is going to be the velocity. And since the velocity is same, because the amount of water passing through the pipe is you could say similar in like every second, because the area is constant, that's why the kinetic energy remains the same. We can write that down in simple words, which is that the velocity and the mass of the water remains constant, therefore the kinetic energy is constant. The velocity and mass of the water remains constant, therefore the kinetic energy is same, or we could write constant. So here again explaining in simple words that only reason why the kinetic energy will increase or decrease is when you change mass or the velocity of the water. Other than that, anything doesn't make any effect, because these are the only two variables in the formula. Either you could decrease the mass or increase the mass, or decrease the velocity or increase the velocity. That's the only way you can change the kinetic energy. And we are done with question number 2. Question number 3. During a picnic on a warm, dry day, a metal can of lemonade is wrapped in a damp cloth. Evaporation cools the water in the cloth. Part A says explain in terms of molecules how evaporation cools the water in the cloth. So for this question, we have to be focused on the words. Okay, it's a really tricky question. So again, we're going to read the question and highlight what is very important for our understanding. So question says, during a picnic on a warm, dry day, so there is no wind, a metal can of lemonade is wrapped in a damp cloth. So here, damp cloth is important, and evaporation cools the water in the cloth. Part A says, explain in terms of molecules how evaporation cools the water in the cloth. This is very important, because when I was doing the question at first, I thought they were asking about the lemonade. But here in the question, it mentions that how evaporation cools the water in the cloth. So for explaining this question, I'm gonna draw something. This is our cloth, and we have hot molecules which are gonna be represented by red dots, and cold molecules are gonna be represented by blue dots. Here we can see, as we have enough energy, what will happen is the red dots will have enough kinetic energy to escape the surface of the cloth, and they will evaporate. Eventually what will happen is all the red dots will evaporate, and we are gonna be left with only blue molecules. We can draw that here on the other diagram. Here we can see that we are only left with blue molecules. Now for this question, there is a specific equation, or you could say a specific formula, and the formula is that kinetic energy is directly proportional to temperature. As we increase kinetic energy, what will happen is the temperature will increase. As we decrease kinetic energy, the temperature will decrease, and it is vice versa. If we increase the temperature, the kinetic energy increases, and as we decrease the temperature, the kinetic energy decreases. Now here we can write this as after, and this is before. We can see here in the illustration, we have red molecules on this side, which tells us that the molecules are vibrating because they have enough energy. And as they're vibrating, that means they have velocity and they have kinetic energy. But on the right side, you can see there are no molecules which are moving. We only have blue molecules which don't have enough energy to cause any change in temperature. So the temperature decreases because they don't have enough kinetic energy. So that's what we have to explain in our own words. I'll take this out for you guys and we can write it down here. So as high energy molecules leave the surface of the cloth, as high energy molecules kinetic energy of the water in cloth decreases. And according to our formula here, this formula, as kinetic energy decreases, the temperature will also decrease. So we can write down here, according to relation, as kinetic energy decreases, the temperature decreases. And this will be pretty much for this question. And for marks, what will happen is they will give you mark for relationship. Second mark is going to be for the molecules leaving the surface of the water or cloth. This is going to be our second mark. And third mark is going to be for like explaining as the kinetic energy decreases, the temperature also decreases. So this is going to be our third mark for part A. Part B says, as the water in the cloth cools, so does the lemonade. Explain how electrons transfer thermal energy through the metal of the can. So for this one also you have to read the question again, as the question asks how electrons transfer thermal energy through the metal of the can. And as we know, metals are solid. And they would probably have, you could say, atoms joined together. Not enough space. It's usually closer than this, but just for illustration, I'm showing you guys this. And for context, we can just draw a can here. And this is magnifying. So what happens is we can see the structure here, and we have free electrons which are moving inside, right? We can represent that as red because it has kinetic energy. Now what will happen is this electron will go and hit with this atom, and this atom will have enough energy to release electron. So this will release an electron, and what will happen again is the electron which has released is going to go and hit the other atom, and that will release another electron. So this is a chain reaction which happens, and we just have to explain the same thing here in the question. So we can write that down here, that atoms present in the metal, atoms vibrate and electrons go and hit other atoms. Atoms vibrate. Eventually what happens is it results in emission of other electrons. Therefore what happens is the transfer of thermal energy occurs. And because of this, thermal energy keeps on transferring and the can will cool down after some time. So we can write down the same thing here. Therefore, transfer of thermal energy occurs. And for this question, you'll get marks based on the first statement, atoms present in the metal, because we are talking about solid. And second mark is going to be for explaining what happens to the electron. So this is going to be for the second mark. You can even draw and explain it in your own words. Here, this is going to be for the second mark. And the last mark is going to be for the fourth line. And this is going to be our third mark. And we are done with question number 3. Question number 4. A thermocouple is a device that is used as a thermometer. Part A says figure 4.1 shows a beaker that contains molten sulfur at an initial temperature greater than 400 degrees Celsius. So this part should be noted that the initial temperature is greater than 400 degrees Celsius. Part I says on figure 4.1 sketch a label diagram for thermocouple that is used to determine the temperature of the sulfur as it cools to room temperature. So this is a pretty basic thermocouple thermometer diagram which we have to draw, in which we have an ice mixture and 2 wires connecting the sulfur and the ice mixture together. So we're just gonna list whatever we need. First of all, we need a microvoltmeter. Second one we need is an ice beaker. Third we need copper wire. And fourth we need is iron wire. So these are the basic things which is needed for thermocouple thermometer. We can draw these things here. First of all, we're going to draw a beaker with ice. We're going to have a beaker here which has ice cubes in it. And second, we're going to have a microvoltmeter circle with MV and 2 wires connecting both the ends. So it's going to be copper, which is going to come from here and connect to the microvoltmeter and inside the sulfur. And the second wire is going to be our iron wire, which is going to connect from the ice beaker directly to the sulfur. And we can label this as well. So this is copper and this is our iron wire, and we have our ice beaker here, and we'll get 4 marks for this. Part 2 says describe briefly how the temperature of the sulfur in the beaker is deduced. So first of all, what you have to do is use the microvoltmeter to measure the EMF. Use for measuring the EMF. And then what you have to do is note the measurement on a calibration graph. And we'll get 2 marks for this. First mark for this and second mark for this. Part B says state one advantage of using thermocouple to measure temperature rather than using a liquid in glass thermometer. So the basic difference between these both is that our thermocouple is low sensitive and our liquid in glass thermometer is high sensitive. So this is high sensitive and this is low sensitive. So what this means is that the high sensitive thermometer will react to maybe, for example, the change of 0.1 degrees Celsius or 0.2 degrees Celsius. But low sensitive thermocouple will react on maybe 10 degrees Celsius or 20 degrees Celsius. So that's what we can write here for our advantage, that it can measure high temperatures compared to liquid and glass thermometer. In glass thermometer. So we'll get 1 mark for this. And we are done with question number 4. Question number 5. Figure 5.1 shows a kitchen tap that supplies instant boiling water. And we can see the illustration here. Cold water passes over an electric immersion heater inside the tap. The boiling point of water is 100 degrees Celsius. Part A says state what is meant by boiling point. So we have to just give the definition of boiling point. So it is a point of temperature where water exists as liquid and gas. And for this one, you'll get 1 mark for mentioning a point of temperature. And second point will be for mentioning that it exists as liquid and gas. Part B says the immersion heater is powered by the mains at voltage of this. When the tap is open, the heater switches on and the current in the heater is this. Part I says calculate the thermal energy produced by the heater in 60 seconds. So what are we given with? First of all, we're given with the voltage, which is 230. Second is the current, which is 13 ampere. And third we're given with is time. And we are supposed to find thermal energy, which is a form of energy. So we can write down everything here to make it simple. So we're given with V, which is 230. We're given with I, which is 13. We're given with T, which is 60. And we are supposed to find E. So the only equation which relates all of these values is P equals IV and P equals E by T. Now what we have to do is we just have to equate them together and make E the subject. So we have E by T equals IV, and we can make E the subject, which is going to be E equals IV into T. So we have the value of I, which is 13. We have the value of V, which is 230. And we have the value of T, which is 60. So we can find out E, which is going to be our answer as 13 into 230 into 60, which is going to give us our answer as 179400, which is same as 1.8 into 10 raised to the power 5. So 1.8 into 10 raised to the power 5. And don't forget to add the units as well, which is going to be joules for energy. Part 2 says the specific heat capacity of water is this. The cold water that enters the tap is at this much degrees Celsius. Calculate the rate at which the water at its boiling point emerges from the tap. So what they give us in this question is the value of C, which is capacity, and T2, which means the temperature at point 2. And we have the initial temperature as well, which they mentioned in the question here, which is the boiling point. So our T1 is going to be 100 degrees Celsius. Now we have our formula, rate is equal to P by C into delta T. So we have to find rate here. We have power, which is energy divided by time. We have capacity, and we have change in temperature. So we just plug in our values. First of all, we have to find out the power. Power equals energy divided by time. So the answer we got divided by 60 is going to be our answer, which is approximately 3000. So we can write 3000, and our power is 3000. So 3000 divided by capacity, which is given here, which is 4200, into the change in temperature, which is T1 minus T2. So 100 minus 22. And this is going to give us our rate. So we can plug this in our calculator. 3000 divided by 4200 into 100 minus 22, which is going to give us our answer as 0.00915. So this is actually 100. So rate equals 0.00915. 0.00915. We can bring this here 1, 2, 3. So this is going to be 9.2 into 10 raised to the power minus 3. So 9.2 into 10 raised to the power minus 3. And we'll get 4 marks for this. Part C says the metal tap is earthed and there is a fuse in the cable that connects the heater to the mains. We have 2 parts here. Part 1 says explain how the earth wire protects the user. So what's the function of the earth wire? We can draw here an example. This is a fuse and this is a wire which has been earthed. So for example, if the current flow in the fuse is too much, what will happen is the fuse will direct that current towards this earth and it will be grounded. So what this does is it actually diverts the direction of the current and it protects the user from getting shocked. So we can write that explanation here. This is pretty much easy. So we can write down here, if the wire has high current, the current will travel to the ground. And that's pretty much the function of earthing. Second part says, explain how the fuse protects the circuit. So this one is really interesting. We can draw a fuse here, maybe let's say this one, and let's suppose that it connects both sides with wire. Now, for example, if we have high current flow in this fuse, what will happen is this wire will melt down and the fuse connection will be disrupted. So what will happen is this wire will melt down and there's no connection in between the fuse. Therefore, we don't have any current flow. What happened is that the wire melted down and there is no path for the current to flow, so that the user is protected and will not get electrocuted. So we can write down here that when the current is high, the fuse breaks and the circuit melts down. When the current is high, the fuse breaks and the circuit melts down. And this is how the user is protected by a fuse. And this was the end of question number 5. Question number 6. Figure 6.1 shows a road next to the sea. Part A says, on a sunny day, the sun warms the road. Describe how the energy from the sun reaches the earth and warms the road. So we can draw here our sun. Maybe we can picture our sun here on this side. And what happens is that the light travels through space and enters the earth. This is the first step. And then what happens is the radiation from the sun travels from the top of the sky to the road and it hits it. And because of that, the road absorbs all the radiation inside. Now this is our second step. The third step is that the molecules inside the road, for example, this is one molecule, it gets enough energy to vibrate. So it starts vibrating here. And this is going to be our third point. So we can write this down here by describing it in our own words. So radiation or light travels through the space from the sun. So light travels from sun through space and enters the earth. Now our second point will be that the radiation from the sun hits the road. And our third point is going to be that the road absorbs the radiation. So the radiation is absorbed by the road. And our last point is going to be that the molecules have enough energy to vibrate, which is mentioned here. So the molecules enough energy to vibrate. And because of this, the road will get warm. So for this question, the marks are distributed on the first part, third part, and the last part, which is going to be the fourth point. The molecules have enough energy to vibrate, and because of this, the road gets warm. and we'll get 3 marks for this. Part B says temperature of the road is greater than the temperature of the sea. The surface of the road is black. Suggest one reason why the temperature of the road is greater than of the sea. As we know that black absorbs the most radiation and emits the least radiation from all the colors. So that's the one reason why the temperature of the road is greater than the temperature of the sea, because it has more radiation in it. So we can write the same thing in our own words, that black absorbs most radiation, the most radiation, and we'll get 1 mark for this. Part C says the air above the road is heated by warm road. Describe how this affects the molecules of the air. Now, for example, our road has hot molecules, or you could say is warm, and we get cold air from this side, which is traveling from right to left on this side. What will happen is that this air will hit the hot, warm, or hot molecule and gain kinetic energy, and this air, which is cold, will also become warm, and it will go up as the density of the molecule decreases. So the same thing we can mention here, that the air molecule gains more kinetic energy, and because of this, what happens is that they move further apart. And we'll get 2 marks for this. 1 mark for the first statement and 2nd mark for the second statement. Part 2 says a cyclist along the road notices that a cool breeze is blowing from the sea to the land. Explain how convention produces this breeze. You may include a diagram if it helps your answer. So when they tell you to include a diagram, that means you must include a diagram. You must, because even if you miss something here in the statement, you could get marked for the drawing as well. So here, as I explained you earlier, what happens is that cold air travels from right to left, from this side to this side, and what happens is that it hits the warm road and it gains kinetic energy. As soon as it gains kinetic energy, what happens is that in the previous questions we have learned that kinetic energy is directly proportional to temperature. As kinetic energy increases, temperature increases as well. So what will happen here is that this air will gain kinetic energy and it will move further apart, and most probably the density of this air molecule will decrease, because density of hot molecule is less compared to a cold molecule. So this will decrease, so that's why it will move up, as you can see here in the illustration as well. And this is how convention works. So it's just a loop. From here it's hot, and from here it's cold. So it's just a loop of convention. So the same thing we can write it here, as molecules gain kinetic energy, the density decreases. And as the density decreases, the hot air moves up. And what happens next is the hot air gets replaced by the cool air. And we'll get 3 marks for this. 1st mark for the first statement, 2nd mark for the second statement, and 3rd mark for the third statement. And we are done with question number 6. Question number 7. Figure 7.1 is a full-scale diagram of a small nail N in front of a thin converging lens. The line L represents the lens. Here, this is the line L, this is XY, and this is the nail N. And you can see the scale here that this one is 1 centimeter. And this height, so 5 boxes is equal to 1 centimeter. Here in the question it mentions the focal length of lens is 3 centimeters, and part A says rays of light parallel to XY are traveling towards the lens. Describe what happens to the light after it passes through the lens. So we have to focus on this. It says that the ray of light travels parallel to XY, and in the question it also mentions that describe what happens to the light after it passes through the lens. So what we can do is that for answering this question, we can do the part B and C first and then come back to this part again. So we're going to do B part first. On figure 7.1, mark and label with an F each of 2 principal focuses of the lens. So here it says that the focal length of the lens is 3 centimeter. So we can count here. This is going to be 1 centimeter, 2 centimeter, and 3 centimeter. From here also this is 2 centimeter and this is 3 centimeter. So we can mark our F here, which is gonna be precisely here, F and F. And these are gonna be our 2 points. Next in part C, it says the small nail N of height this is positioned 2 centimeter to the left of the lens. Part I says by drawing on figure 7.1, find the position of the image I of N and add image I to the diagram. So this is our small nail N. We have to draw a diagram here. And in the question, it says here in part A that the ray of the light parallel to XY are traveling towards the lens. So there is a ray which is traveling parallel to XY, which is going to be here, and it passes through the lens. Now what's going to happen is this ray is going to pass through the focal point, which is going to be here like this. Next, what is going to happen is this ray is going to go back as well. So we're going to draw the back ray as well here. Now the second ray is going to be from the nail itself, and it's going to pass through the center point of the lens. So it's going to be like this, and both rays are going to be away from each other on the right side. So we can draw back the lens, the light as well, which is going to be here, and they eventually meet. Yeah, they probably meet somewhere here. So we can draw our image I over here, and we can label this as I. And we get 3 marks for this. Now we can do the part A, which says describe what happens to the light after it passes through the lens. First, what happens is that the light meets on this point, right? And then what happens is the light travels from this point till the center of the lens, the converging lens, and then it separates its way from each other. And it goes in different direction like this. So the same thing we have to explain in our own words. So we can start writing for this. The first point is going to be all light meets at the point. So all light meets at a point. The light travels from the point through the lens. And then what happens is eventually it passes from the focal point and separates itself. And we'll get 3 marks for this. So the marks distribution is going to be for the first one, second one, and the third statement, respectively. And we are done with part B and C as well. Part C2 says explain and state whether I is real or virtual image. Of course, it's going to be virtual because it's enlarged, and you can see that the size of original nail is way smaller than the size of the image projected. So we can write down here that it's a virtual image, and the reason is going to be because the ray do not meet and the size of the projected image is way big. Do not meet after passing from the lens. And this is pretty much you'll get for 1 mark. Part 3 says state the name given to a lens when it is used in this way. So you can see here that the original object is way smaller than the projected image. So this is usually used for magnifying something. So this is specifically called magnifying glass. And we are done with question number 7. Question number 8. Figure 8.1 shows 2 vertical cylindrical tubes and a cylindrical magnet all held in a vacuum. This is a plastic tube and this is a copper tube, and we are given with cylindrical magnet as well. So it's better to draw a field line around the cylindrical magnet, and we can move on next. One tube is made up of plastic and the other tube is made up of copper. The 2 cylindrical tubes have identical dimensions. The magnetic field of small cylindrical magnet is extremely strong. Initially, the magnet is at rest at the top of the plastic tube. The magnet is released and it falls through the plastic tube without experiencing a resistive force. The magnet takes this much time to fall to the lower end of the plastic tube. Part A says the mass of the magnet is this. Calculate the kinetic energy of magnet when it reaches the lower end of the plastic tube. So we can see here that, for example, if the magnet was kept here, initially it was on the top and then it moved down here. So what happens is that the kinetic energy is increasing and GPE is decreasing of the magnet. That's what we have to use here. Kinetic energy equals GPE, which is gravitational potential energy. So our kinetic energy is going to be equal to mgh, and we are given with the mass here, which is 0.012 kg, and we're given with the time as well, how much time it takes for the magnet to go till the end. So we can plug in our values, whatever we have here. So our kinetic energy is going to be equal to mass, which is 0.012, and gravitational constant is 10, and we need to find height. Now, how do we find height? We know that we have an equation for this, which is S equals ut plus half at square. That's how you find the length. So S equals u initial velocity, which is 0. So that's why this part will become 0. So we have half a, which is 10, and then t, which is going to be our time, 0.67 square. So we can put this in our calculator, and we'll get our answer as 2.2445. So our S equals 2.2445. Now when we plug in our height here, which is going to be equal to 0.012 into 10 into 2.2445, we can just multiply these two values with 2.2445. So here into 10 into 0.012, which is going to give us our answer as 0.269, which is approximately equal to 0.27 joules as its kinetic energy. So 0.27 joules. Part B says that the magnet is then held at the top of copper tube and released. As it falls through the copper tube, an electric current is generated in the copper. Explain why there is a current in the copper. Now there are two fields. First field is the magnetic field of the magnet, and the copper tube has its own field surrounding the site. What will happen is when the magnetic cylinder is kept on the top, this magnetic field will cut the copper's field, and because of this what will happen is an EMF will be produced. So we can write down that here, that the magnetic field cuts the copper field, and because of this an EMF is produced, and we'll get 2 marks for this. Part 3 says the current in copper produces a magnetic field of its own in the tube. The magnet falls much slowly in the copper tube than in plastic tube. Explain why the magnet falls more slowly in the copper tube. So the reason for this is because Lenz's law is applying in this. The Lenz's law only applies on metal, not on plastics. That's why the Lenz's law, I can explain it here. The Lenz's law, it's spelled L-E-N-Z law. The Lenz's law is there is always a force on a magnet, which is like trying to oppose the motion of the magnet. So the same thing we have to write here, like Lenz's law means force on magnet. So we have to explain this here as well, like force opposing the motion of the magnet. Lenz's law means there's a force opposing the motion of the magnet. And we'll get 2 marks for this. First mark is going to be for telling that it's Lenz's law, and second mark is going to be for explaining what happens. And the reason why it doesn't affect on plastic tube is that plastic is not a metal and copper tube is a metal. So this law doesn't apply on non-metals. This is non-metal and this is a metal, and therefore this law applies only on copper in this case. And we are done with question number 8. Question number 9. Combinations of logic gates are used when digital signals are processed. Part A says describe the difference between a digital signal and an analog signal. You may include a diagram if it helps your answer. So first of all, we are going to draw the diagram because it's really important. So first we are going to draw the diagram for digital, and then we are going to draw it for analog. So here we have 2 boxes. For digital, we have high input as 1 and lowest input as 0. And for analog, we have our variable signals. So for the first one, we can draw as 0, 1, and then 0, and then 1. This is how a digital signal looks like. And for analog, we have our variable signal. So it's going to be something like this. It's not accurate, but it's going to be like this. So we can write our description down here that digital sound consists of ones and zeros. An analog signal consists of continuous variable. And we'll get 2 marks for this. Maybe 1 mark for diagram and 1 mark for statement. Or if you only write the statements, then you'll get 1 mark for this as well. So it's going to be our 2 marks. Part B says figure 9.1 is a truth table for a logic gate X. Here we can see the truth table. Name the logic gate X and draw the symbol that represents it. We have to name it here and the symbol is given. We have 3 basic logic gates, which is AND, OR, and NOT. So this is definitely not a NOT, so it's going to be cancelled because NOT only needs 1 input. And we have to use these both and check what it gives. So first of all, we can use is 0 plus 0, which should be 0, and 0 plus 1 should also be 0, 1 plus 0 should also be 0, and 1 plus 1 should be 1. And you can see the output doesn't match with this. Even if we put NAND, which is opposite of AND, we get the output as 1, 1, 1, 0, which is definitely not the output given in the truth table. So AND is not an option and NAND is not an option here. Now we have to use OR gate. So we can use OR gate here with orange. 0 plus 0 should be 0, 0 plus 1 should be 1, 1 plus 0 should be 1, and 1 plus 1 should be 1. And we can see the output here is completely opposite of what we are getting for OR gate. So it could be NOR gate. So we can check that here. If we take opposite of this, we get this output. So it's NOR gate. And the symbol for NOR gate is, so we have our 2 inputs, and we have our simple OR gate, which is going to be like this, and our circle in the front to represent not OR, and we'll get 1 mark for this. Part C says logic gate Y is identical to logic gate X. So these both are identical. Draw a combination of logic gates X and Y that behaves like an OR gate. Label the input A and B and label the output as Q. So they're saying that both of these are identical. So we have to combine them together. So we have 2 OR gates together, which is going to be like this, input A and B, and we have our OR gate, and this output is going to split into 2 because we have to combine the other gate as well, which is Y gate. We can write this as X, and we're going to draw the Y as well. So this is going to be our input for Y, and this is going to be our output Q. So this is going to be Y. And if we draw a truth table for this, we can see it's the same as OR gate. So we'll get 2 marks for this. And we are done with question number 9. Question number 10. 2 of isotopes of hydrogen are hydrogen 2 and hydrogen 3. Part A says state one similarity in the composition of their nuclei. So as we can see here, they both have same number of protons. So we can write here, both have same protons. Or we can write same proton number. Part 2 says describe how a nucleus of hydrogen 3 differs from a nucleus of hydrogen 2. So for this, we can see here on the top. So the nucleon number of hydrogen 2 is more than nucleon number of hydrogen 3. So we can write down that here. That hydrogen 3 has more number of neutron than hydrogen 2. And we'll get 2 marks for this. Part 2 says in a nuclear reactor, a nucleus of hydrogen 2 fuses with the nucleus of hydrogen 3 at an extremely high temperature. This fusion reaction produces an isotope of element X and releases a neutron. Part I says explain why an extremely high temperature is needed when forcing these 2 nuclei together. So first of all, we're going to highlight the most important things which the question mentions. The fusion reaction produces an isotope of element X and releases a neutron. And the part I says explain why an extremely high temperature is needed when forcing 2 nuclei together. So as we know that both hydrogen are positive. Both are positive. If you force them together, they both will repel each other. That's why we need extremely high temperature to fuse them together. This is what we are going to explain in this question. So first of all, what we are going to write is both hydrogen are positive. And then we are going to write as that they repel each other when brought together. Therefore, high temperature gives enough kinetic energy to do the work. And we'll get 3 marks for this. First mark for mentioning they both are positive. Second mark for mentioning that they repel each other. Third mark is that we need high temperature so that we can do the work. And even in this question, they're using the formula E, kinetic energy is directly proportional to temperature. So part 2 says, using nuclide notation, complete the equation for this reaction. And here we can see that the question mentioned that it releases element X and a neutron. So these both are reactant on the left side. We have to write the product. So when these two hydrogen isotopes react or fuse together, they release X element and a neutron. So nucleon number for neutron is 1, and a neutron doesn't have a proton, so it's going to be 1 and 0. Now doing the math, you can see this is 1 plus 1, which is going to be equal to 2, and 2 plus 3, which is going to be 5, but then 1 goes here in the neutron. So that's why we're going to make this as 4. So this is going to be our nuclide notation. We just write this for 2 marks, and we are done with the last question. I hope this video was really helpful to you guys. If you have any questions or any doubt, you can ask me in the comment section. I'll try to respond as soon as possible. Till then, see you in the next video. Bye bye.